Okay, so good morning. We moved from leading-edge commercial companies to leading-edge universities. So we moved from what you can do today to what you can do tomorrow. I'm moving on from the product to what is the reliability of banks in the next 10 years. And we moved from banks to cloud. You know, cloud is transforming the banking. This is actually a quote from IBM Expert Advice. Cloud is transforming the banking. The cloud is changing the financial industry. We all know that our data are not on a single computer, not on a single machine, but are in the cloud. What is the cloud? Well, it's very difficult to say, but you know, it's something that is intangible, it's something that is around the world. You also know that cloud can fail. Now, you can expect, you know, well, what happens, you know, has ever happened to you to have a problem with your bank or software failures? Well, this is actually something that I like to show you. Failures in the cloud are unavoidable, okay? This is a very, very short essay of failures in the cloud involving not banks. It involves many different companies, very large companies, companies that you expect actually to be fairly reliable, strongly reliable, and this caused a big amount of problems. You know, we're talking about big numbers, talking about billions of dollars per year lost in cloud failures. And financial software is not bug-free. So we have, okay, I picked up a very cherry picking, you know, just get to Google, you know, the David, get a couple of you know, search for cloud problems in banking, you know, and pick up the first list. So nothing to do with any of this, you know, every bank can be listed here, you know. This is HSBC. Millions of banks customers were unable to access their account offline due to a software problem. This is, again, SBC, 250,000 of individual payments failed to be processed because of a problem with the software. This is Bloomberg. Bloomberg software glitching down for 2 hours. 2 hours downtime is billions of dollars lost. Again, a combination of hardware and software failures. This is RBS, my first bank, by the way. You know, I'm a bit scared about that. RBS, Royal Bank of Scotland, 500,000 payment failed for a software problem. So basically, I don't want to scare you, but what my job is to try to figure out how do we actually deal with this huge problem, which is we are moving, you know, we will have failures. A problem which is not just me individually, is all the society, all the community, all the banks, because one failure affects not so 1, 2, 3, but millions of people. And that's what we are doing is, here in Schaffhausen Institute of Technology, we are trying to actually move on and do leading-edge research, which I inherited from my former group, and is actually what we call self-healing cloud system. Sergey mentioned this idea of the self-healing body. You know, you cut yourself and your body actually reacts to the cutting, to the cuts. You actually have a problem and your body reacts at a given amount. That's exactly the problem. We are living in an environment that the cloud is actually moving, is changing, is not controllable anymore. It runs on any machine. You don't know even where it actually is. And so the idea is there is no way, no matter who you are, and I'm coming for 30 years of experience in software testing, you know, so test, we get the bugs, remove bugs, it's perfect. No, it's not. No matter how much you test, bug is there. So the idea is to move from design, from development, to the field. It's mimic, if you want, the human body. You know, you cut yourself, the body actually reacts. You have a software bug. What we do is we prevent, we tolerate, we remove failures before they happen by predicting, locating, and working around the failures. So the very core idea of our work is: can we actually be able, instead of being shocked by that actually 1 million customers not being served, be able to actually step down and say, okay, in an hour, it will be a failure. Let's actually take care of that before it actually harms the system. And what we do is, well, by the way, there is a lot of things on the cloud. So what we do is not just something that is there. There is a lot of things. If you are in the technology, you know, this is actually technology, OpenStack technology is cloud technology, Kubernetes is a leading edge cloud technology, and you have here a list of tools, a list of approaches that help you to monitor hardware and system recovery for pods. So there is a lot of elements so that the cloud is really stable and reliable. But performance inference, if you run these kind of tools, many of them actually slow down your system. Not everybody runs the system all the time. There is absolutely no knowledge about the status. You have no idea whether the system is failing or not. It's simply trying to make sure that you actually balance without knowing whether there is an obstacle. And there is no knowledge about the application. Why is actually a problem with the bank? Why is a problem with the system? They don't know. Now, what we are going to do is we are moving from the limitations to the features. What we have is we want to have an approach which has limited performance inference, with an approach which has a knowledge of application composition, which has, in a nutshell, a holistic vision. You want to see the whole part. It's not just the system, it's not just the cloud. It's our system that you should actually hear. And we started basically the idea that we have, and we call the system STAR. STAR because it's the name, the historic name of a labs. I actually started 3 labs. This is the 3rd one, and I like this idea of this name, Software Testing and Analysis Research Lab. And basically you actually have activate the fault. So whenever something happens, there is a failure, a fault, a bug in your software. Okay? And at some point it can be there silent for many years, for many decades. And sometimes it happens that it actually is activated. And you enter an error state, so the system is not correct anymore. And then there's a failure. Now what we do is we want to predict the failure before the failure itself. We want to actually localize the fault. So it's not just prediction. What's funny, because we started working with a large company, and we said, oh, we can predict the failure. And can you tell us where? Well, no, but it's somewhere in the system. We do have 20 million nodes in our system. How the hell, can help us if you actually say it fails, You want to know where. So we want to locate the failure, at least in the cluster. And then we want to heal, and so that the failure disappears and the system runs correctly. And that's what we do. How we do that? We monitor the system. So what you have is you actually sense and act on the system. And then we walk through 3.5 steps. Predictor, localizer, healer, with monitor. Monitor is standard, so we didn't do anything. We just inherited that. You have the cloud, you get all the kind of monitors you can find, long list of elements, KPIs you can monitor. Okay, what we want to do is we want to work on the new technology. Predicting failures. Now, I have different instances of them, because we started with this one, which we call the 1.0 at this point, right now, which is basically great. We take data analytics, we take machine learning, you combine the 2 of them, and you can really predict the system. So how we can do? Basically, you can detect anomalies, and you can actually classify anomalies. And what you do is, it's simple. Complicated technically, but intuitively simple. You look at every single metric in your system, and you see there is a big hole there. So it's a single anomaly. Single anomaly can be that there is the SIT day today, and many people come here, and it's anomalous because you have many more connections than usual. So that's, number of bucket sense in this room right now is much larger. Okay, now what we want to do is we want to go ahead and actually try to understand whether the anomalies is good or bad. Now you say, who cares? It's anomalous, you just raise your hand. If you just do that, you raise your hand always, because there's always something anomalous. So we use a different kind of technology, which is machine learning technology, deep autoencoder. Deep autoencoder is the technology that allows you to basically distinguish between bad and good anomalies. And this is what happens. You have the blue ones, which are the spurious anomalies, good ones. And you have the red ones, which are the failures. Okay. And what you do is, autoencoder allows us to draw that little line, which tells you whatever is above is okay, whatever is below is bad. Few outliers, but you see we have a precision which is over 99% to actually get it. So we get great failure prediction and fault localization. We went to our customer, our first customer, and they say, look, it's easy. You just run your system for a couple of weeks at least, and you inject a couple of million faults, and then you can actually build a good model and then to predict the faults. Can you imagine the reaction of the people? Say, are you injecting faults in our system? I don't tell you which bank was it, but the guy was sort of shocked, you know. Are you expecting us to inject failures for 2 weeks in our system just to build your model that will tell us later whether we failed or not, or no way. So we moved on. We moved on with machine learning only. It gave up because the training is actually the heavyweight of data analytics. And we get the second predictor, which is fairly simple again. It's called one class support vector machine for the one who are in technology. It's a fairly sophisticated machine learning approach. It's a black box, you know. You, of course, a black box with millions of parameters. You set up all the parameters correctly, and then you get to the point, and you get very, very high precision. But you pay the non-training with only failure alerts. You have failure alerts, you don't know where it is. So basically what we get precise prediction, but no localization. Fortunately, without seeded faults. So step 1, okay, great, but we cannot apply that. Step 2, we can apply that, but we miss something. So we went on with the third part, which is energy-based models. Now, we listened this morning to the Nobel Prize lecture from a physicist. I started this work with a postdoc of mine. She is a theoretical physicist. When I hired her, the people in the group also said, look, are you joking? You know, we get a theoretical physicist in a software engineering group. Let's try that. And Christina, that's the name of my friend, she came in and said, oh, you know, how does superconductivity work? Well, yes, you know, you get a lot of speed in superconductivity. No, it's very simple, you know, it's, you have all these atoms, and you have the spin, and when the spin aligns, then the matter becomes a superconductor. What has this to do with testing, you know? Can you give me a feeling, you know? Oh, it's simple. You get all these KPIs, can be anomalous or not anomalous. When they align, you get an anomalous state, which is not the superconductivity, is the failure. So it's a very specific state. And so we actually used the Ising model, okay? Basically, Ising got a Nobel Prize for that, by the way. So, and we build a baseline model again. You look at the things and you actually say the green area is where you actually are safe. And then you actually, when you are out of the green area, you have what is called an anomalous energy, and then you can actually predict with a precision and a recall which is fantastic, and the performance is fantastic. So we get to the point that we have, again, precise value failure prediction, no fault localization, no overhead, and online incremental training. Your bug changes day by day, week by week, month by month, and we follow it. So at this point, we have this very nice idea that you can actually press the button, get it running, and whenever there is something which is getting wrong, where you have. And we moved on with fault localizer. Yet another technology, KPI ranking. Okay, KPI ranking basically is exactly what Google does. If you think about it, you know, you search for SAT, you get maybe 2 billion pages now, okay, and you want to get the right ones, okay? So basically, how you get the right one? Well, it's a fairly sophisticated algorithm. It's called page ranking, which actually, given some elements, tells you what are the list of the priority list. And so you get the first hit, the second hit, the third hit, which usually works very well. We do the same with KPIs. What we do basically is we build a graph that actually represents the correlation among KPIs, and then we actually see what this is the correlation. We see how they correlated, and we actually compute the correlation between the anomalous ones. And this gives you not only the prediction, after the prediction it tells you where the system is. So you basically have what is called a time series. You see, time by time, 1 anomalous, 2 anomalous, 3 anomalous. The anomalous grows very fast. At the same point, you stop and you say, okay, look, it's not just a failure, it's a failure in that node, in that application. Okay, and we have fantastic accuracy again, okay, and you see with many different failures. So, prediction 1, 2, 3, long training, but not very useful. No training, good. No training, evolvable, fantastic. Failure, fault localization, the pair gives you not only the prediction but also the localization. And now the healing, and I'm done. Okay, assume you actually have your system that tells, look, you're failing. Look, the failure is there. Most of our customers are already happy. But we want to do much more, which is we use natural language processing. What is natural? What has natural language processing to do? Think about what are the information, what is the information you actually find in your system. It's written informally. So we read blogs, error reports, tutorials, and we locate what is called automatic workaround. We do what you do manually. If something is failing, you don't fix that immediately. You try to get a workaround that helps you surviving. And so what you do is you get, for example, that you can get from the information like a thread is found to know that it is equivalent to search from danger. And this is going to be done automatically using word embedding and word over distance. And so basically we can actually automatically not only know that the system will fail, not only know where it will fail, but also know what to do else, what else to do to avoid the failure. And so we have extensive experience with failure prediction, we have extensive experience with machine learning, we have preliminary experience with workaround. Extensive experience means we have commercial partners. We have a company based in Basel who is selling a product which is based on this technology. Okay, so it's very nice to see theory, application, and product. And what we will do next is actually going from the static configuration we're dealing now with a highly configurable system and with a very pervasive approach. And so, what we have today is SIT, which is doing research in this area. Bertrand is speaking in the other room, so you will not hear him. And I'm speaking here, and I'm working on software quality and cybersecurity. You get the program, you get the environment, you get the people, and you actually get reliability and protection. As Sergey mentioned and Chris mentioned, we started 3 months ago. We do have, I am personally amazed how we I could not believe we could actually build this big event. We are hiring desperately. We need good people, good scientists, good students, good companies, good partners. We do have many, but more is important. Thank you.
Thank you, Mauro. This is the first time I see this presentation, and I'm quite impressed because, frankly, I mean, you explained it extremely well, but I don't understand it fully. So
that was the goal, actually. You know, I want to give you the feeling of actually how difficult it is. I think the question is not when you can do something. You can actually put together enormous amount of technologies, and that's exactly the multidisciplinarity you mentioned. That you get machine learning, you get deep learning, you get natural language processing, you get cloud, you get software engineering, you get all together in pretty good way.
But is what you're doing here, is this a module that you introduce into systems, or you program it into the system?
It's research, it's ideas. Okay, so you're talking
you
about
have a marketable product.
Yes, well, not me actually, our partner. The partner is actually, it's a service basically. What you do is you have your cloud system, okay, and you add yet another service, which is the self-healing service. So basically it means it's software that you add to your system. Practically speaking, you actually have one node, extra node, one computer, that actually you get probes that actually look at the different metrics, and the node tells you with a very nice console, okay, what is going well, what is going well, not that well, what is going bad, how it fades, and when it fades, and how to do what.
Cool. So anybody else understand it more than I did?
What's the company's name in Basel? What is it called?
IC Information is called. It's a small company working in Basel on IC Information.
Is this system live, meaning that you have a status quo right now, you are in a company set of software, types of software running, then obviously the company has evolved, changed the software, add new modules. Is this following up what is happening, or you need to reprogram?
No, it's a following up. So the idea is the company, we need to work with money, of course. Research is not free. I need to pay students, I need to pay the postdoc, I need to build the system. We do have our own little cloud system where we do experiments. We cannot experiment directly on the bank systems, for example. And we do that. We need support for people who actually are interested in the technology. We need also support of people who know or want to use the technology. So we started, this research has started with companies who were actually Now they are our users. They really had a problem. They wanted to actually modify their system. They wanted to actually act on the system so that they wanted to get more reliability. In the specific case, what happened is that in this long list, we actually had 3 or 4 major sponsors so far. We actually had this company who decided to invest in the technology to be able to go on the market. And that leg of the system was shared properly between us and the company, and they decided to get the product. So they do have a product which is not based on the latest technology, by the way. It's based on the second type technology, because that's a mature one. The third one, the energy-based technology, the KPI ranking is still, I'm a bit reluctant to actually go directly on the market with that. So basically, it's a sort of follow-up. They put money in the research to give us the chance to actually get the ideas and the results. We do experiment in the lab. They follow up and they decide what has to be done in the market, what cannot be go to the market, what is too early, what is good enough, what is the market. It's not my job. In fact, if I get them here, they have a fantastic day. You get this big console with all these numbers, all the colors going up and down. I only have this big diagram. It sounds like a bit rare, a bit strong. But basically you transform that into, you have a full picture of your cloud, and you see what is normal, what is anomalous, what is deeply anomalous, what is getting bad, when it fails, what happens, what to do, what is the problem, how to heal the problem. And I don't know if I answered the question.
Yeah.
Good. We need to move on. Thank you, Mauro. That was very interesting.